Greetings and welcome, friends. We were talking about like vectors and translations and stuff like that yesterday, and chickens. Just a moment of silence for Ryan's chickens. Thank you. This video is in memory of them. It says, name the vector and write its component form. So this looks like the vector. Ooh, I was going to go back to my classic yellow, but you know what? It kind of matched the color almost. I'm going to roll with it. So this is going to be vector ST. And I put this little harpoon symbol up top, so it's not an arrow indicating it's a ray, it's a vector, and it's from S to T, not from T to S, because the direction matters for vectors, which vectors, by the way, had both direction and magnitude. But we were able to write them in component form, where we had kind of like these awesome angle brackets, which I'm assuming you could use for all sorts of like little text-based faces or something. But what we do is we break this up into its horizontal component and its vertical component. So it looks like -2, left 2, and -4, if I count right. So -2, -4 is the component form of said vector. All right, ooh, here we go. So it says find the component form of the vector that translates from P to P prime, and here they gave us P prime. So vector P prime is going to be component form. Let's see, what happened to the x coordinate here? Yeah, it went right, left 1, so I'm going to call that -1, and then for the y coordinate, up 2. So our component form vector is going to be something like that. You probably could have just had this, but I realized we had the ability to name it proper, and it deserves a name and an identity. -3 to -4 was moving to the left. It became more negative. Let's see. Write a rule for the translation. So I can just kind of pick any of these points as reference. So it looks like from M to M prime, it's going up 1 and over 3. A rule for the translation is this. So x comma y becomes x plus 3. Oh, I should have gone over and then up, shouldn't I? Comma y plus 1. So that's how you write a rule for the translation. Meh. There you go. We also talked about how translations were rigid transformations, where the side length is all the sides maintain their congruence, all the angles maintain congruence. The triangles themselves are congruent to one another. Good stuff. Good stuff. Ooh, looks like I gave us a giraffe here. Let's see if I can plot some points. Over 2 up 4 is x. Y is over 6 up 0, y, and z is over 7 up 2, so there's z. I could try to draw a triangle here, but that was actually a pretty good line. I'm proud of myself for freehand in that. So let's see. This looks like, it's a function. It's a composition of transformations, both translations. So let's we'll denote this one in orange, I guess. So the translation, if I add 12 to the x, so 2 becomes 14, and then I'm adding 4 to the y, so up 4, 1, 2, 3, 4. This would be x prime. For z, adding 12 to 7, man, wow. It's over to 19, and then up 4. Nope, I misplaced it, didn't I? Man, Mr. Wade, be better at your job. Right, and then up 4 from 2 is going to land us at 6. All right, so there's z prime. And for the y, 6 plus 12 is 18, and up 4 is 4 from 0. So here's y prime. And then I'm going to translate yet again. From x prime, I'm translating to x double prime. So from here, I'm going to now -5 and -9. So -5, 1, 2, 3, 4, 5. Yeah, and then subtract 9 from, what is this, 8, so that's going to bring me down to -1. So this is going to be x double prime. Actually, I'll label this on the top here. Let's see, for the z, I'm subtracting 5 from 19, that brings me to 14, and subtracting 9 from, looks like 6, so that's going to bring me down to -3. So there's z dub prime. And for y, I could actually do the translation, or I also just noticed that y is like left 1 down 2 from z, so I'm just going to go left 1 down 2 and cheat just a little bit. Although that's not really all that much cheating, is it? It's just using the fact that translations are rigid transformations, and compositions of rigid transformations will also be rigid. And let's see, that's all they wanted us to do, right? Yeah, I did it, done. I could then create a shorthand that would just jump from this to that if I wanted, which actually, well, we're here. We're all here right now. If I wanted to do that, it looks like for z, it would have gone, this would be like the shortcut translation, cut out the middleman of the prime here. It looks like this would have gone over 7 and down 5. So the shorthand translation would have been x comma y is going to be mapped to x plus 7 comma y minus 5. Which also, notice, is what I would have gotten if I combined these, which makes sense. That makes a lot of sense. Two translations could be summarized as a single translation in this case, yeah. They didn't ask us to do the purple one, but I was just pointing out that we could, that we had the ability to. Aha! All right. Here we go. So, all right, let's talk about this. So here we've got, it says, try to prove the corresponding angles theorem using properties of translations to prove each theorem. So I'm going to mostly just verbally do this, so you guys can just follow along. That'll be fine. I didn't, right. So you could start by drawing a doodlegram of a situation. It didn't have to look like this, and labeling things can be helpful. You can give things names all you want, just because then you can have a means of communicating about those things, right? So I've got a little sketch here. What does the corresponding angles theorem tell us, by the way? Does anyone remember? If I have two parallel lines cut by a transversal, then their corresponding angles are congruent. Okay? So what I'm going to do is imagine using translations. What if I map line AB and line BD along the vector BD? All right, so this entire thing would just go right, and it would get mapped like so. BD would map onto itself, right? If I shift the line BD along ray BD, it's still going to be the same. Point B would now map onto D, right? And this angle would map onto this angle perfectly. All right, those lines would actually, AB and CD would be the same line. And since translations preserve angle measure, if these angles now match up exactly when they're translated onto one another, when I untranslate back, they would also have been the same. So that's kind of like the way you would describe this, all right? Translations are rigid transformations, and so the angles formed by AB and BD are congruent to the corresponding angles formed by the original setup. So that's kind of like the idea, is if I mapped this over here, those angles would have been the same as they were before they were mapped. So that's kind of the explanation. All right, well, thanks for watching, Internet friends, and if you would like to donate to the Ryan's Chicken Fund, he'll add a comment in the post below. All right.